Okay, let's unpack this. We know tackling climate change demands massive action, specifically drastic cuts to CO2 emissions. And when we say drastic, we mean getting well over 90% below current levels.
That's right.
But even with those huge reductions, some emissions will inevitably remain. Think about sectors that are just incredibly hard to decarbonize.
Exactly. And that's really where carbon dioxide removal, or CDR, comes into the picture. It's the set of solutions needed to address those, leftover emissions.
So, pulling CO2 out of the atmosphere or biosphere after it's already there.
Precisely. It's a crucial part of the climate puzzle, but, and this is key, only after we've done everything possible to cut emissions first. It's not a replacement.
Right. Absolutely not a replacement. And we have a source here that takes a really granular look at these CDR technologies. It's a study titled Assessing Carbon Removal Technologies, Integrating Technical Potential with Environmental, Social, and Governance Criteria and Sequestration Permanence.
Quite a mouthful, but important.
It is, and our mission in this deep dive is to really get into this study. We want to figure out how a group of experts evaluated 16 different CDR technologies, what specific scorecard they used, and what that tells us about the actual quality of these options, looking beyond just, well, whether they can remove carbon.
Right, because as this study makes crystal clear, while technical feasibility is obviously the starting point, it's far, far from the only factor that determines if a technology is actually a viable climate solution in the real world.
So let's set the stage properly with the challenge, as laid out in the study. Climate models consistently show we need to cut current CO2 emissions by over 90% to meet those global warming targets, like 1.5 or 2 degrees Celsius.
Yes, that's the absolute priority, non-negotiable. And the remaining, let's say roughly 10% of emissions, from heavy industry, maybe aviation, agriculture, things like that, those are the ones where CDR solutions are really needed to compensate and help us get to net zero.
And this study also helpfully clarifies the terminology, which, let's be honest, can get a bit confusing sometimes. It draws a line between carbon capture and utilization, CCU, or carbon capture and sequestration, CCS.
Right, the ones that happen at an emission source, like a smokestack at a power plant or a cement factory.
Exactly, capturing it before it gets out.
And CDR, carbon dioxide removal, which is the specific focus of this study we're looking at. CDR solutions are fundamentally different. They're designed to pull CO2 directly from the ambient atmosphere, or say from biomass that captured atmospheric CO2 through photosynthesis.
So it's actively reducing the concentration already in the air.
Yes, rather than just stopping more from getting there from a specific point source.
Yeah.
A key difference.
Okay, that distinction is really important. Now let's talk scale. This study references other research, and the numbers are pretty staggering. The global technical potential for CDR is estimated to be massive. Figures range anywhere from 11 to maybe even 200 gigatons of CO2 removal per year globally.
Which is potentially huge. I mean, for context, this study estimates the actual need for CDR, assuming we hit that 90% emission reduction target by 2050, is around 4 gigatons per year.
Okay, so 4 needed, potential maybe 11 to 200.
Exactly. So purely from a technical, can we do it standpoint, the world likely has the potential capacity to meet that requirement many, many times over.
That sounds incredibly promising on the surface. But as this study immediately pivots to technical potential, well, it's not the full story, is it?
Not even close. Whether these technologies can actually be deployed at the scale needed depends on so many other crucial parameters.
And assessing those other parameters is really the core contribution, the main point of the research we're digging into today.
Precisely.
All right, so who exactly did this evaluation, and what kind of process did they use to arrive at their conclusions?
Well, this assessment was carried out by NG's Scientific Council. It's actually quite a diverse group. You've got experts with interdisciplinary backgrounds, drawing from both academia and industry, and importantly, representing different regions around the globe.
So, an international panel bringing both theoretical knowledge and practical industrial experience. That sounds robust. And the method they used was the Delphi panel methodology. Can you briefly explain what that involves?
Sure. It's essentially a structured communication technique. The goal is to build consensus among a panel of experts, especially on complex or uncertain topics where there isn't a single right answer. It usually involves a series of, let's say, questionnaires or surveys combined with feedback rounds.
Okay.
So the experts provide their initial judgments, then they see the group's aggregated, anonymized responses, and they can revise their own views. It helps move the group towards a converged, more considered opinion.
It sounds like a really rigorous way to get experts potentially with different starting points, to agree on more subjective criteria, like, well, like the ones we'll get into. And this wasn't a quick weekend workshop either. This study notes the whole process ran for a full year, from May 2023 to March
A
2024,
whole year, yeah.
and involved face-to-face meetings, online discussions, all specifically aimed at building that consensus on both the assessment criteria and the actual findings for each technology.
Yes, they definitely put in the time to reach a thoughtful, shared view. And they focused their evaluation on three key dimensions for each of the 16 CDR technologies they looked at. First, the estimated technical potential we just discussed. Second, a really comprehensive set of environmental, social, and governance criteria, ESG. And third, sequestration permanence.
Permanence, okay. Basically, how long the captured CO2 is expected to stay locked away and out of the atmosphere.
Exactly. How durable is the removal?
Okay, let's dive into what this study proposes as its core metric for comparing these technologies. This quality measure. This seems to be their way of packaging some of those crucial non-technical factors together.
That's right. The quality measure, as defined in this specific study, is essentially a combined score. It's derived from two main components, that ESG score we just mentioned, and the sequestration timescale, or permanence.
Right. And the ESG score, they put it on a scale of 1 to 5, right? With 1 being the worst in terms of ESG impacts and 5 being the best. Why did this study place such significant emphasis on ESG within their quality metric? It seems quite central.
It is, and as the authors explain, ESG performance is just absolutely critical.
Yeah.
It directly impacts the social acceptance, the practical viability, and ultimately the legitimate use of these technologies. I mean, think about it. For many CDR options, especially newer ones, there are still significant uncertainties,
Okay.
big unknowns about their potential environmental and social consequences.
Mm.
Things like land use competition, water requirements, impacts on biodiversity, effects on local communities, equity issues.
Right, all that stuff.
All that stuff.
Hmm.
These factors can introduce major risks and barriers to actually deploying a technology, even if, technically speaking, it worked perfectly fine at removing CO2. So ESG performance isn't just a nice to have.
No, it sounds fundamental to whether something can actually happen at scale without causing other major problems. Okay, that makes a lot of sense. What about the permanence component then? The sequestration timescale?
So that's about how long the CO2 is reliably kept out of the atmosphere once captured. This study categorized permanence into three basic tiers. Less than 100 years, between 100 and 1,000 years, or greater than 1,000 years. Obviously, from a long-term climate perspective, longer is generally considered better.
Makes sense. More durable storage. And how did they actually combine these two, the ESG score and the permanence tier, to get that final quality score?
So this study used a specific weighted calculation. They made a conscious decision to give the ESG score slightly higher weight than the sequestration timescale value.
Oh, interesting. Why?
Their stated reasoning for this weighting was really the urgency of the climate crisis, the need to find effective solutions that can actually be deployed realistically within the next 3 decades. They felt that assuming a minimum sequestration period is met maybe 30 years, which most options aim for the immediate environmental and social hurdles captured by that ESG score, were perhaps a more pressing concern for near-term deployment feasibility than whether the storage lasts 500 versus 1,500 years.
That's a fascinating choice. Prioritizing the getting it done soon without major screw-ups factor slightly over the lasting forever factor, given the urgency. Okay, so what was the actual calculation?
The formula they used was quality equals the ESG score, 1 to 5, multiplied by 1.5, plus a value for the time scale. They assigned 1 point for the 100 years tier, 2 points for 100 for 1,000 years, and 3 points for 1,000 years.
Got it. ESG times 1.5 plus 1, 2, or 3 for permanence.
Exactly. And when you look at the results presented in this study, particularly in their summary tables, you see a pretty wide range of these quality scores across the different technologies.
So what came out on top? Which technologies got high-quality scores?
Well, according to their assessment, direct air carbon capture and sequestration, or DACCS, came out highest with a quality score of 9. Also scoring well were reforestation and using wood for construction, things like mass timber buildings, both scored 8.5, and biochar, which is like charcoal used as a soil amendment, scored an 8.
Okay, those top ones sort of feel intuitive, maybe. High-tech capture, using nature like forests and wood, or creating stable carbon in soil with biochar. But you mentioned a wide range, so I assume some technologies scored quite low.
Yes, very low indeed. According to this panel's assessment, several ocean-based technologies were judged as having particularly low quality. This included things like ocean fertilization,
Yeah.
inducing ocean upwelling, ocean alkalinity enhancement, and also cultivating CROPS for bioenergy combined with ocean storage of the CO2.
Wow. And what score did they get?
They all received a low-quality score of just 3.5.
3.5 compared to 9 for DCS. That's a huge drop. What drove those scores down so dramatically in this study's view?
Well, according to the paper, these low scores were primarily driven by receiving the lowest possible ESG score, a 1 out of 5. This reflected the expert panel's collective assessment that these particular ocean-based methods currently have the highest degree of uncertainty surrounding them,
Okay.
and therefore the greatest potential for unknown, possibly significant negative impacts on marine life, ocean ecosystems, and overall biodiversity. There's just a lot of ongoing scientific debate and considerable concern about potential unintended consequences when you start intervening in vast, complex ocean systems at scale.
That makes a lot of sense. The potential risks and the sheer number of unknowns in those really sensitive, complex environments would definitely weigh heavily on an ESG assessment. Were there technologies that landed somewhere in the middle range, not top, not bottom?
Yeah, absolutely. Technologies like mineral carbonation, which involves reacting CO2 with minerals to form stable carbonates, and enhanced weathering, basically speeding up the natural rock weathering processes that absorb CO2, they landed in the middle. Also, direct ocean carbon capture and storage, or DOCCS, which is different from the others I mentioned, these all had quality scores around 7.5. So, yeah, the study definitely shows a whole spectrum of perceived quality based on these specific criteria.
Okay, so this study provides this quality score, combining ESG and permanence. How do they then suggest integrating this information with the technical potential for actual decision making? It's one thing to have the score, another to use it.
Right. What they do is present the technologies visually, often using charts or figures. These typically plot the quality score, that combination of ESG and permanence on one axis, against the estimated technical potential by 2050 on the other axis.
Oh, okay, so you can see where each technology falls in that two-dimensional space.
Exactly. It allows decision makers to visually categorize the technologies.
Yeah.
Is it high potential and high quality?
Right.
Or maybe high potential but currently low quality due to ESG concerns?
Yeah.
Or perhaps lower potential but high quality, that kind of thing.
And they layer on a third crucial piece of information in those visuals too, don't they? Something about readiness.
Yes, exactly. They add the technology readiness level, or TRL. This is a standard scale used to indicate how mature a technology is. It ranges from basic research ideas, which would be a low TRL, maybe TRL2, often shown in red in their
Yeah.
figures,
Right, early stage.
all the way up to technologies that are fully demonstrated and commercially available, which would be a high TRL, maybe TR9, often shown in green.
So combining quality, potential, and readiness level, that seems incredibly practical. How does this integrated view actually help different types of decision makers? Who uses this and how?
Well, this study suggests it helps tailor strategies. For instance, a company or maybe a government agency that's looking to invest in and deploy CDR solutions right now, or in the very near term, would likely focus heavily on technologies that score well on both TRL, meaning they're mature enough to deploy, and this quality metric.
Makes sense. Ready and relatively good.
Right. Conversely, someone who's planning a longer-term climate roadmap, maybe looking out towards net zero targets decades away, they might consider broader portfolio. They might look at technologies with lower TRLs today that need more R&D investment now, but which perhaps offer very high potential and could achieve high quality in the future if the ESG issues are resolved.
So it helps you balance immediate needs with future possibilities. It's about understanding the trade-offs across multiple important dimensions, not just one.
Precisely.
And okay, what about cost? That feels like the elephant in the room. It wasn't built directly into this study's quality measure, but it's obviously a huge factor for any real-world deployment decision.
Absolutely, and the study acknowledges that. They state clearly that cost is a critical selection factor, even though it wasn't part of their calculated quality score. They do discuss estimated cost ranges for the different technologies elsewhere in the full paper.
And what do they say about those costs?
Well, they highlight that these cost estimates currently have very, very large ranges. There's still a lot of uncertainty, especially for less mature technologies. So cost adds yet another layer of complexity and uncertainty for anyone trying to make investment decisions today.
Yeah, sounds familiar for emerging climate tech. And bringing it back to the overall scale, needed that target of around 4 gigatons per year of removal needed by 2050 after the big emissions cuts. This study emphasizes that even technologies that might seem smaller in terms of their individual potential are still vital, right?
Yes, exactly. The required removal is significant. 4 gigatons is a lot. So achieving that target will almost certainly require a diverse portfolio of solutions working together. The study makes the point that even technologies with estimated technical potentials that are below that total need,
Like biochar, maybe.
like biochar, which they estimate around 2 gigatons potential, or using wood materials in construction at maybe zero point 0.4 gigatons, according to their figures.
Yeah.
Even these are really valuable components of the overall mix needed to get to that 4 gigaton goal. It's not just about finding the single biggest solution. It's about assembling a mosaic.
Okay, so pulling together the key takeaways then from this deep dive into this specific study.
I'd say the main points highlighted are, first, that the global technical potential for carbon removal solutions is estimated to be well above the projected need by mid-century. So technically, it seems doable.
Okay.
However, when you start assessing these technologies based on this quality metric, integrating the crucial environmental social governance criteria and how long the carbon actually stays removed, you find there's really wide variability across the 16 different options they evaluated. Some look much better than others on these fronts right now.
And because many of these technologies, especially some of the newer or less understood ones, like those ocean methods, still have significant unknowns regarding their full ESG impacts, this study strongly emphasizes the need for more focused research, right?
Yes, absolutely. A major conclusion coming out of this study is a clear call for increased scientific investigation, specifically aimed at better understanding and, importantly, quantifying the full range of ESG impacts, both positive and negative, for all these CDR technologies.
Mm.
And crucially, exploring how any negative impacts can be effectively mitigated or avoided altogether.
And they keep coming back to that absolutely critical principle throughout the study, especially in the conclusion section.
It seems non-negotiable in their view, and frankly in the broader climate context, CDR options must be deployed as a supplement to, and absolutely not as a substitute for, drastic emission reductions.
Yeah.
Those 90% plus cuts have to happen first.
Yeah.
Using the idea of future CDR to somehow justify delaying emission cuts or prolonging our reliance on fossil fuels fundamentally undermines the entire goal of addressing climate change. CDR comes after the primary reduction efforts have been maximized. It cleans up the remainder.
A very clear and crucial point. And ultimately, the authors of this study, they express a hope for how their work might be used, don't they?
They do. Their hope, as stated in the paper, is that their proposed assessment method and the resulting ranking they developed will serve as a valuable tool, something that can help inform both future research priorities, where should we focus R&D, and also current decision-making processes by governments, investors, companies.
So guiding the way forward.
Exactly. The overall aim is to help guide the selection and deployment of carbon removal strategies so that they're not only effective at removing CO2, but also legitimate, appropriate, and socially and environmentally sound, given the scale and urgency of the climate challenge we face.
So we've taken quite a deep dive here, guided by this group of experts using that rigorous Delphi process into how 16 different carbon removal technologies stack up against each other. We saw how they looked beyond just the technical potential, can it suck carbon, to create a more nuanced quality score, critically evaluating those environmental, social, and governance factors alongside the crucial question of how long the carbon actually stays sequestered.
And hopefully understanding these different dimensions helps you, the listener, really appreciate the complexities and the inherent trade-offs involved when we talk about different climate solutions. It highlights that it's not simply about building a technology that can work on paper, but it's also critically about its real-world footprint, how it impacts communities and ecosystems, and whether the climate benefit it provides truly lasts.
Yeah. So the technical potential appears high, globally speaking. And this study gives us a pretty robust framework now to assess the quality based on those crucial ESG and permanence factors. But here's something to think about. If we have the technical know-how, potentially, and we now have a better way to assess quality, what are the biggest challenges that still stand in the way? Maybe it's the economics, maybe it's policy development, maybe public acceptance, or even just building the sheer infrastructure needed. What needs to happen to ensure the right mix of these CDR solutions actually gets deployed at the necessary scale, in time, and crucially used correctly as that supplement to deep emissions cuts, not a dangerous replacement? Something to consider as this whole field continues to rapidly develop.
And just to remind everyone, that study was titled Assessing Carbon Removal Technologies, Integrating Technical Potential with Environmental, Social, and Governance Criteria and Sequestration Permanence.